Hello everyone, these are a few videos which I've put together to hopefully explain the arrangement of electrons in atoms and where we get the evidence from. So there is a series of these, and hopefully this will help you to understand and explain quite an abstract concept when you have to. So the arrangement of electrons, of course, begins with the basic idea that we have a nucleus at the center of an atom which is dense and positive, and then the electrons are added to that from the innermost shell closest to the nucleus, and we work outwards from that. So each time we add electrons, we get further away, of course. So essentially, the arrangement of electrons that you know about from GCSE is that we have electron shells. Well, there are other terms which are equally useful for those things, and these are they. Electrons are arranged in shells. We can also call them energy levels or even quantum levels. And the first new piece of information is that electron shells are made up from subshells. Now, the subshells that we're going to come across, there's a simple relationship between the electron shell number and the number of subshells. Shell 1 has 1 subshell, shell 2 has 2, shell 3 has 3, and of course shell 4 has 4 subshells. Now there are different types of subshells that we have to get used to. These are referred to as S, and then P, D, and F. Now don't worry what those letters mean, but I could explain, but I'm not going to. The actual subshells themselves are increasingly complicated in terms of their appearance and structure. We only have to know the appearance of S and P subshells, and we'll see that shortly. Now, within each electron shell or subshell is our simplest unit of electron structure, which we call an orbital. Now, an orbital is a region in space around an atom that can hold 2 electrons maximum, which have opposite spin. Now, this means that the 2 electrons, if you like, spin in opposite directions and never actually meet each other because, of course, they would repel. So the idea of representing our simplest idea of electron arrangement as an orbital, a cloud, if you like, that contains 2 electrons that spin in the opposite direction, is pretty much where we start with. So we're going to have a look at the arrangement of electrons and how the subshells, shells, and orbitals are all put together. So first of all, let's look at shell 1. Energy level 1. This is closest to the nucleus, and as you probably would realize, we can only accommodate just the 2 electrons. Well, because it's shell 1, we have our first S subshell and our only orbital, and this will only hold a maximum of 2 oppositely spinning electrons. So at the bottom of the table, we designate this 1, which is the energy level or shell 1, S, which is the subshell type, and 2 is the maximum number of electrons it can hold. So hydrogen and helium are 1s1 and 1s2 when the electrons are in place. Shell 1 is now complete. So let's move further out from the nucleus and we come to shell 2. Well, according to the pattern, of course, shell 2 has 2 different subshells. These are called 2s and 2p. Well, within the 2s, of course, we just have the one 2s orbital, and as you can see, it is a spherical shape with 2 oppositely spinning electrons. Now, a 2p subshell is composed of 3 separate orbitals. We designate these 2px, 2py, and 2pz, and as you can see, they are an hourglass or dumbbell-shaped thing composed of 2 parts, and they occupy obviously mutually perpendicular positions on x, y, z axes, so they all, if you like, fit together. So within our second shell, have a look at the table, we have 2s and 2p subshells, we have a 2ps or 2s orbital, and 2px, y, and z orbitals. In terms of electron filling, the 2s holds 2, and each of the 2p orbitals, of course, can only hold 2 each. So we add together the 2 and the other 6 from the p to make 8 overall. The The designations for shell 2 are 2s2 and 2p6. So at the moment, when we're adding up our electrons, we've now added the 1s2 and now 2s2 and 2p6. We're up to 10 electrons altogether, and this, of course, is the arrangement for neon. Now, when we get to shell 3, of course, the picture gets much more complicated. And of course, according to the pattern, there are 3 sub-shells. These are called, as always, 3s first, then 3p, and we introduce 3d subshell. Well, of course, again in the pattern, the s orbital, 3s, there's one of them. There are 3 mutually perpendicular p orbitals, 3px, 3py, 3pz. And then we come to our rather unusual 5 d orbitals. And these, don't you worry about the designation. You'll never be asked the identity of these things, just the fact that there are 5 of them. And you'll never be asked the shape of them because it's quite a complicated looking thing. For example, look at the last one of the green things, 3dx squared, which of course is a bizarre looking object with a central ring or torus around the middle of it. So never mind the actual shapes. We don't do that in A level. We do use them in 3D orbitals when we look at transition metals in year 2. In terms of electrons, as always, each orbital can hold a maximum of 2. So when we add up the total number of orbitals in the third shell, of course, we have 9, 1s, 3p and 5ds. Altogether, maximum number of electrons, of course, is 18. Now, shell 4 would be very, very complicated to draw and show, so I haven't done. So what I have done is I've converted this information into a single table, which I think we've already seen, or at least I've shown you. So here is our summary table, and as you can see across the top, shell 1, 2, 3, 4, and so on. The subshells follow the nice pattern, 1 for shell 1, 2 in shell 2, 3 in shell 3, and 4 subshells in shell 4, and obviously 5 in shell 5. The orbitals again follow the same pattern, 1 in the S and 3 in the P, 5 in the D, but in the new one in pale yellow there are 7 F orbitals in, of course, the F part, F subshell. Well, if you follow the pattern, then there would be 9 orbitals, and that would be the G subshell, but we don't mention that. In terms of electrons, you can again follow the patterns. 2 in shell 1, 2 and 6 makes 8 in shell 2, 2, 6 and 10, 18 in shell 3, and 2, 6, 10, 14, 32 in shell 4. Well, without worrying about it, we can actually predict the number of electrons that would be in shell 5 because it follows a nice little arithmetic pattern. 2 plus 6 makes 8, plus 10 makes 18, plus 14 makes 32, and of course plus 18, add another 4 on, would make 50. So the pattern is clearly very important. The fact that it works, the fact that it repeats, is fundamentally significant. It means that the arrangement of elements in the periodic table follows this pattern exactly. And if you look at the order of filling diagram underneath here, then this is a very popular picture and tells us a lot of information. Well, what I've done is I've broken the dotted lines which separates the shells 1, 2 and 3 and 4 from each other. I've also put the S subshells as the grey diagram, grey boxes to the left. The P subshells are in the pink, and the D subshell that you can only see, the 3D subshell, in orange. Now, each of these boxes, as you can see, the little squares, they represent an orbital. And we use a very simple symbol as a half arrow head going up and another half arrow going down to represent the population and filling of each orbital. This is known as an orbitals in boxes diagram, and you do get asked to draw and represent and label these things, quite straightforward. The important thing is the red arrows. These actually show you the order of filling. If you like, this is filling up from the bottom, and as the further up you go, the further away from the nucleus you become, the further out the electrons are, the closer to the edge of the atom the electrons are. And of course, the original energy levels of course are explained by the sequence. If you follow the order, this shows you the order in which these orbitals are and subshells are filled. So from the very beginning, 1s2, then we carry on to 2s2 and then 2p6. That completes shell 2 as well. That was neon. We then start shell 3 with 3s2 and then 3p6. And here comes the interesting changeover. Before we complete the third shell with the 3d subshell, we start the 4s subshell. Because it's slightly lower energy than the 3d, it gets filled first. So after 3p, we go to 4s. Well, of course, that corresponds to the 20 electrons in calcium. So what comes after calcium? Well, of course, the first element of what we call the D block, or some of which are transition elements, the element scandium. Well, scandium is representing, as you can see, by the addition of one more electron into the now empty, vacant 3d subshell. And that is the next subshell that we start after calcium. So we've got from scandium through to zinc. We are filling up that 3d subshell by adding electrons to the 5d orbitals. If we complete the pattern, we end up going from 3d then to 4p, and 4p6 is up to the element krypton. If we started the next shell, will be shell 5, following the pattern beginning before we finish shell 4, then that would be the next two elements, of course, rubidium and strontium. So effectively, when we come to add electrons, you can see we've got a definite pattern, we've got definite arrangements. Now, just to remind you, the two subshell orbitals that we actually have to be aware of. The shape is, of course, fairly simple. An s orbital is drawn spherically. In other words, don't just show a circle, but shade it to make it look three-dimensional, because it is more sphere-like. And then a p orbital, you could draw it as a figure of 8, as you can see, or a dumbbell or hourglass shape. But again, shade the thing to make it look like it's three-dimensional. And you can see it consists of two parts, or two fuzzy patches in the image. So those are the two orbital pictures that we need to draw. And when we put the orbitals together, like I said, we have, for example, shell 2 showing here, where we have the spherical S subshell with the 1s orbital, and then the 3p, x, p, y, p, z orbitals that all fit perpendicular to each other. So that's what shell 2 would look like if you could see it. Now, the arrangement we see on the table here is a very useful diagram. This is the energy level diagram, which shows the energy of the electrons as each subshell and orbital is filled. We start off with the lowest energy, 1s, and then we start to fill shell 2 with 2s and the 2p subshells. We then go to 3s and then 3p subshells. But notice the energy level of 4s is slightly below that of 3d. So we start filling 4s, and then when that's filled, we go now back to the inner third shell to complete that with the 3d subshell. And then, of course, to 4p, and we would end up going after 4p to 5s, but we don't really have to go any further than krypton. So that arrangement of electrons we can now show you step by step. This diagram shows how the electrons would be added or would be filled in our complete set of electron shells, subshells, and orbitals. And you're going to see the electrons dropping into the boxes, the orbitals, and you can see them as oppositely spinning arrows. So when we put the other subshells and shell boxes, orbitals in place, we get a familiar arrangement of the subshells and the orbitals. And of course, you can see the furthest left column, we've got the s orbitals for each energy level or shell. And then we've got the p subshells, which consist of 3 orbitals, x, y, z. And then we've got the 5d orbitals, as you can see in the 3d region as well. We would then add the 4s, which remember is filled before the 3d, so that is why that one goes in and shaded red, you can see that. Then 4p, and then of course 4d and 4f would come up later on. We don't have to worry about that far up the arrangement. So we're going to add electrons to this, and so when we do so, we'll watch them dropping in from above. So we're going to fill the lowest available energy level first, so watch carefully, and pop it in. There goes the first electron, and then the next electron will go oppositely spinning and will drop in with that. So then we've got a completely full first electron shell. This of course is 1s2. We then go to shell 2, starting this s subshell with its s orbital, and I add the 1 and then the spinning paired electron to make a full 2s. Now we come to the filling of the 2p subshell. They do ask the questions on this principle quite readily. When we add the electrons to the 2p or 3d subshell, same thing happens. When we put the electrons in, so here goes the first electron. Now the second electron, we would have a choice. Do we either pair up with the oppositely spinning electron in the same orbital, or do we place our next electron in an empty vacant orbital? Well, the principle is called Hund's rule, and it says simply this: electrons will only pair up in the same orbital if there is no empty orbital available in the same subshell. So in other words, the second electron goes into an orbital all by itself, and there it goes. So single occupancy comes before pairing, okay? So there is the second p electron, and there goes the third one. Now, after the 3p electrons have been added, we are half full. And so in an ideal situation here, there is an electron in each of the x, y, and z orbitals, all mutually perpendicular, all keeping separate and far away from each other as possible. When we come to add our fourth p electron, we have no choice but to pair it with one of the others in the same subshell. So when we come to p4, we have no choice but to start pairing. And this spin pairing arrangement, as it's called, does destabilize the electron arrangement. It's not particularly happy to spin and pair up 2 electrons in the same space because of their repulsion for each other. 2p5 does that again, and when it comes to 2p6, then we've completed first and second shells, and we've added 10 electrons, and here we are at neon, which of course is a very stable electron arrangement with 2 completely full shells. Shell 3 is starting now with sodium. There goes the first electron. As you can see, it has 1 outer electron. It's in group 1. It would therefore obviously lose that 1, showing a +1 oxidation number in order to be like the neon arrangement. Magnesium would be the 3s2, second electron in place, and of course that's in group 2. Would get rid of both of those to form 2+ ions and be like neon again. And then we come to the next arrangement. So the third electron to be added, we recognize now comes from the 3p subshell, and this of course is aluminium. And again, losing all 3 of the available electrons in the outermost shell, shell 3, would allow it to form a 3+ ion. And you can see where lots of these well-known things are now starting to fall into place. Silicon and of course phosphorus. And then we come to the same position we had previously. We have to add a 4th electron into the p subshell. This same thing happened in shell 2. We now have no choice but to spin pair my next electron in sulfur, and this is it. There's the p4 going in, having to pair up in the same, if you like, px orbital. another one for Py, and then when we complete the 3s and 3p, we've got now a picture which of course is argon. And this is 18 electrons, and again a noble gas, just like we had with the first full shell, which was helium, 1s2. The first and second full shells was neon, of course, and now we've got the first, second, and, well, not quite completely filled, but certainly a full 3s and 3p subshells, which gives us argon. And now comes the interesting bit. Remember, we have a slight dislocation, if you like, in our pattern, because the 4s orbital is slightly lower energy than the remaining 3d. So when we come to add electrons, the 4s fills before the 3d. So we get potassium, and then we get calcium. Now, what actually happens now is when these have now been filled, the 4s now moves slightly above the 3d level. On the 3d levels drops slightly lower. So now the next available one would be the 3d, because that's the next available position. So when we add these electrons, 3d1 will be scandium, and then titanium and vanadium, and then we get to chromium. Now, chromium does an interesting trick. In order to preserve the most stable electron arrangement, chromium is able to make a single electron occupy each of its 5 d orbitals. The way it does this is by promoting one of the paired 4s electrons into an empty position in the 3d subshell. So when the chromium gets the next electron, which gives it 3d4, watch out for the little shift from the 4s to unpair that and put the next electron to complete the 3d with 5. So watch carefully. Now, if you spotted that little horizontal shift, the electron dropped in, and then the 5th electron moved across from 4s to 3d. So why is that so special? Well, of course, look at what we're left with. 4s1, that's a half-full orbital with no spin pairing, and now we've got 3d5, all 5d orbitals with a single occupant and no spin pairing. So half full is a very stable arrangement, just as well as completely full. So if you like, completely full is the best thing to have, half full is the next best thing to have, and incomplete, which is neither half full or full, is probably not a great thing to have in terms of electron arrangement. So the next additional electrons, of course, must carry on being added, and the only available lowest energy position is back in the 4s2, and this would be the manganese arrangement, 4s2 and 3d5. Well, again, with no option now, whether we like it or not, we have to start spin pairing with the d electrons. So after manganese, we get iron, and we get cobalt, and then we get nickel. And when it comes to copper, we get that same shift again. The next electron would go in there to give 3d9 with one spare place. And as with chromium, copper does exactly the same thing. Watch out for the 4s electron shifting across to complete the 3d subshell with its 10th electron. So in goes the copper electron first, and then the shift across from 4s to give us 4s1, which is half full, and of course 3d10. Half full and 3d10, which is completely full, is far more stable an arrangement than the 4s2 and incomplete 3d9 we would have had. So the arrangement shifts across to give us a more stable pattern and a more stable electron arrangement. So remember, there were 2 elements that did this, chromium and copper. It's easy to remember because they both begin with the letter C and feature a letter R in their name. So chromium and copper do this 4s electron shift, as you can see, to give a more stable picture. Following the extra electron being added in to give us a zinc, well, zinc has the outer shell 4s2, just like calcium. No surprise then that zinc and calcium have got very similar chemical properties. Their outer shell, 4s, is just 4s2. Same with calcium, same with zinc. Remember, the 3d electrons belong to a full now inner shell, the third shell. So after we've got as far as zinc, we will complete the 4p subshell with, of course, gallium and germanium and arsenic, and now spin pairing selenium. So that same p spin pairing pattern, we've already seen it twice before. The first time we saw it in the 2p subshell was with oxygen. The second time we saw it was with sulfur, and now the third time we've seen it is with selenium. Well, of course, what we're showing you, oxygen, sulfur, and selenium, are the elements in the group 6 of the periodic table, the oxygen family, the elements underneath oxygen. So, of course, being as predictable as it is, the periodic table, then no surprise we would expect that same P4 pairing arrangement to happen again once more when we come to the element below selenium, which of course is tellurium. So when we do finish up, this of course is bromine with 4s2, 3d10 and 4p5, one more electron, which gives us the krypton arrangement, which is again another noble gas picture. So our pattern of arrangements, as you can see, and we're now going to show that all again, but this time the shorthand electron arrangement, the 1s2, 2s2 business, and the identity of the atom itself. So we've seen a few of these. So let's begin. 1s1 will be hydrogen. 1s2, of course, is just helium, and now that shell is full. Shell 2, 2s1, which is lithium, after 1s2, and then beryllium, which completes that 1s2, 2s2. After beryllium, element number 5, of course, is boron, 1s2, 2s2, 2p1. And the next one with no spin pairing, single occupancy, carbon, 1s2, 2s2, and 2p2. Nitrogen is where we have our single occupancy in each of the 3p orbitals, 1s2, 2s2, 2p3. And like I pointed out, the oxygen is where we get our first case of spin pairing in a p subshell. We carry on by adding electrons. There's fluorine, one electron short of a completely full neon arrangement. No wonder fluorine is so reactive. It will do anything it possibly can and does to get that one electron. It doesn't matter who it gets it from. It will steal electrons from its mother if it could. So after the fluorine is finished, when we add the next electron, of course, we get noble gas neon, and everybody wants to be like one of these. Sodium is a little bit thwarted. It's got an electron it doesn't really want. It doesn't want that 3s electron, so no wonder it's so reactive. So when elements are as close as they can be without being a noble gas like fluorine or sodium, then they are very reactive indeed in a desire to either gain an electron in the case of fluorine and of course get reduced, or lose the electron as in the case of sodium and get oxidized. So redox is basically facilitating elements in their ability to get to be like a noble gas by gaining or losing the electrons. And the closer the elements are to noble gas, the more reactive or vigorous their behavior is in actually getting there. So when we get to 3s2, magnesium, group 2, loses both the 3s electrons to be like neon. And then aluminium would ideally like to get rid of 3 electrons, 3s and 3p, in order to be like neon. And of course it starts to get more difficult. Losing electrons is no easy thing, because each time we add an electron on, we also add a proton into the nucleus. So aluminium has got 13 protons and 13 electrons. And getting rid of an electron, giving it 12 or giving it 11 or even giving it 10, still means we still have 13 protons. And the electrons that are left are increasingly strongly held by a stronger effective nucleus. So after aluminium, no spin pairing silicon, which of course is the same pattern we saw with carbon, 3s2, 3p2 in the same group, of course, as carbon. And then we found our single occupancy of the P subshell, 3P. Last time we came across this was 2P, 3 was with nitrogen. Unsurprisingly, the element below it, phosphorus, does exactly the same arrangement. And of course, it's now getting much more difficult to get rid of 5 electrons to be like neon. And so what they tend to do now is the opposite. It's much easier to actually gain electrons to be like the next noble gas, in this case would be argon. So phosphorus will ideally gain the 3 remaining electrons to complete the 3p subshell, forming a p3 minus ion, which of course is electronically just like argon. So when we actually do this electron arrangement, p4 spin pairing, just like we saw with oxygen, this is happening again with sulfur as the pattern predicts. And then the one before the noble gas, this time chlorine, well, of course, it's not quite as reactive or quite as dangerous as fluorine, because the electron shell that it's gaining an electron in is further from the nucleus. It's also what we call shielded or blanked or blocked by the second electron shell. And shielding of full inner shells is something else which we have to take into account when understanding and explaining the arrangement of electrons, as you'll see. And when we add the last of the 3p electrons to give us 3p6, we now have, of course, got the noble gas argon. And so the patterns appear to happen when we fill S and we fill P subshells, we end up with a noble gas. So after argon, remember, look at the electron in boxes energy level picture. The next available orbital is, of course, part of shell 4, the 4s subshell, the 4s orbital. Then goes the potassium electron, group 1, of course, wants to get rid of that electron to be like argon, the previous noble gas. And of course, then calcium. Calcium's outer shell arrangement, you can see its full configuration, ends with 4s2, and so therefore it has begun the 4th shell. Well, once we've got to calcium, we then know what happens next. We start to fill the 3d subshell by adding the electrons in the correct order of filling, single occupancy first, and as we do, we go from scandium, titanium, vanadium, and when we get to chromium, remember, we would have 3d4. Well, then we get the 4s that shifts across to give us the 3d5 and 4s1 arrangement. So there goes that little shift, and as you can see, chromium manages a much more stable arrangement with 2 half-full subshells with no spin pairing. And then after chromium, manganese, and we follow a pattern again, iron, cobalt, nickel, and of course copper, which would have been 4s2, 3d9. The d9 is not a happy arrangement at all when we can have a d10. So we'll shift the next 4s electron across, and again we get that unusual arrangement or anomalous arrangement. It's not like the others. 4s1, 3d10 is the outer arrangement with copper. And then zinc, remember, has an outer shell of 4s2, just like calcium had. And so no wonder the outer shell is where the electrons are gained and lost, where the actual chemistry is concerned in the outer shell. And so the outer shell arrangements of zinc and calcium are 4s2, and so no wonder their chemistry is very, very similar. The difference is that zinc has a lot more neutrons and protons, and of course d electrons in the structure inside that 4s, which means all that extra mass makes the zinc considerably more denser than the calcium. We get a very similar picture with the elements underneath zinc in the table, which of course will show that end of the periodic table when we get to the D9, D10 area. Those elements get substantially more dense. So zinc, cadmium and mercury, and one before that, copper, silver and gold, of course familiar for their incredible heaviness and density. Well, after we've completed our arrangement for zinc, we'll go ahead and finish the 4p subshell with gallium, of course, germanium and arsenic. Spin pairing at P4 again, after oxygen and sulfur we get with selenium, and then the noble gas just about got there, bromine. Bromine again is a 4p5, like chlorine was 3p5 and fluorine was 2p5. Almost, but not quite getting to noble gas. And again, as you can see, the 4p electrons are further away than the 3p ones and the 2p ones. There is an extra load of shielding, protection, if you like, masking of the nucleus from the fourth shell. And that shielding makes bromine's ability to pull in one more electron that little bit weaker than chlorine, than fluorine. And that arrangement is very important in group 7 chemistry. Okay, so when krypton is complete, we've got all of the electrons up to 4p6. Now, just to remind you a couple of the issues, the electrons enter the lowest energy level orbital that's available. So as you can see, follow these on the periodic table from the 1s, which is hydrogen and helium. Then we go 2s, lithium and beryllium, 2p, all the way, of course, boron to neon. The 3s, sodium, magnesium. The 3p is, of course, underneath that. That's aluminium up to argon. And then 4s is potassium and calcium. And then the 3d is the element sequence at scandium through to zinc. And then the 4p is the last chunk we have to worry about, which, of course, is gallium up to krypton. Hund's rule, remember, this was electrons occupy orbitals singly and only pair up when there's no other alternative. So single occupancy before pairing, and spin pairing is less desirable than single occupancy. This leads to some of the issues we're going to come across. Now, what you're left thinking is, how the devil do we know all this? How does this all come about? How have we got the idea of subshells and shells and orbitals and filling and all this kind of stuff? Well, much of the evidence comes in our next video, which is going to be the video dealing with the first ionization energy. Now, when we do ionize atoms, we lose electrons. And the very simple principle is, just like when we add electrons from the inside working outwards. When we lose electrons, we lose the outer shell electrons first. So we'd lose outer shell 4 before inner 3d. We'd lose outer shell 4 before any other inner electrons go after that. So 4s electrons must be lost before 3d. As, of course, when the electrons are added, the 4s moved above the 3d to make sure it's in its outer shell position. So very simply, when you take electrons away, you work backwards. You remove electrons working inwards towards the nucleus. There were two exceptions to the arrangement of electrons. These were chromium and copper, where we occupy the orbitals in a much more preferential half-full arrangements rather than an inadequate, incomplete subshell. So chromium was 4s1 3d5, not 4s2 3d4, and copper was 4s1 3d10, not 4s2 3d9. Okay, so I'm going to stop the video because the next one is all about the evidence, and you're going to see that shortly.